In the previous lecture, we have fixed, as usually, the algebraically closed ground field and fixed, together with the natural number, the genus, and we have introduced the two basic objects of our investigation, the moduli spaces of curves over K and that is called the coarse moduli space, and let me remind you that it is I would like to say the set for every K and every J. And besides that, there was mentioned a more complicated object, the fine moduli. Perhaps we will also call it moduli space, but it is not a set, it is the topology. I also write though several topologies are used to define this object, perhaps we are going to choose one of them. So both of them were hinted about but not defined completely. That is, this was defined as a set, but the structure of the quasi-projective variety was promised but not given, and here the idea was formulated, but the precise definition not given, as well as for the whole concept of topology, only the preliminary one was given. So we start here and define the most important part of this moduli topology. What we have introduced there in relation with this object was there were three B's, and sorry, I have forgotten which one, perhaps like this, was fixed as the category of bases. And then for the object of these categories, the families of curves were defined. the families of curves were defined, and these are the open sets. We'll call them the opens, in fact, without quotation marks, but with the image of them, not like the open subsets of a fixed topological space, but rather as some kind of coverings. This is just a picture to imagine the objects, but to give a true definition, we need to define the morphisms. The morphisms of well, perhaps I'd rather write it once, not omitting anything. And the basis, which is most important, that the bases are different here in the morphisms. And well, of course, instead of the classical inclusion that I'll try to write down here, the inclusion of one open set into another, we have to define the class of morphisms here, and it is done in the almost obvious way, or I would say in the expected way, like this. So it has to be the morphisms of everything, and well, let us write down the details. First of all, let it be here F and F. Well, there is no standard notation for the family. Let's try to draw it like this. Here is one family of curves, and here is another. Let me think for a while how to draw the fact that it is another. Well, maybe I'll try to use a non-standard trick. So imagine that, not quite good, yes. Well, let's just draw the fibers closer to the base. Then we'll have, sorry, I'm telling about it in the lecture form for the first time. So the picture is like this. At least we see that it is this morphism is something like covering. So what I'm not sure about, whether we are going to, whether we'll need notation for the morphism of the bodies of the families themselves, but if we consider it set theoretically, the most important condition would be that X is isomorphic. Well, in the same category in which the bases live, though the families of curves mean, well, mean the object of the same categories together with the morphisms and the condition of the fibers we have formulated. So the square should be a square of the base change of B with X prime over B prime, just in the usual way. And sorry, there are three conditions. Do I have places for everything? So I'll try to, no, I have no, so let's first write, yes, I need it. Now I see that I need that the letter here, and F is supposed to be fiber-wise, isomorphic. That means obviously that for any B, note the fonts, any point B of the base, the fiber X sub B is isomorphic to the fiber of X prime over B prime and B bold. No, not bold. And this isomorphism is established by the restriction of F to what? To X sub B. So the conditions are rather restrictive, and the third one that is maybe the most important, morally important, is that F is supposed to be étale. And let's give a separate definition F for some other letters not used here, say from Y bold to Z bold is étale, means again two things. First, that for any Q in Z. Let me remind you that everybody here uses, well, the small letters corresponding to the notations of the schemes. Well, here Y and Z are schemes. K schemes. But I leave, say, the small y's and z's for the sections of the structural shapes, well, for the functions over pieces of y and z. So for any q of z, scheme theoretically or just set theoretically, the pre-image is finite, and so when we have, let's denote by P, so for any pre-image of that Q, we have the pullback morphism of local rings, and it is some kind of ring extensions, but these local rings are DVRs, discrete valuation rings. That means simply that there is a topology defined by the powers of the maximal ideal, so it's written everywhere, and it induces the morphisms of the completions of these rings, and it is supposed to be isomorphism. So this long algebraic definition is the analog of the definition of being the local homeomorphism over C. So this is, a rather long definition of the one of the main topologies we are going to work with. I think just because of its length, we are mostly going to work with it onto the intuitive level, and let's remind ourselves that the coarse moduli space is defined by the following obvious construction. Whenever we have a family of curves, where do I write it usually? Drawing I didn't it yet, so to the left, say. So there is a mapping. Here we work clearly in the category of sets over the category of sets. Mapping every B, let's draw it here. Here is B, here is the fiber over it, and it is mapped to a point here that is the isomorphic class of the corresponding fiber in MG. So let me remind you that we have discussed the desirability of the moduli space of curves that would represent a family functor that associates to every base the set of classes of isomorphisms of families of it, but it does not exist, and maybe I cross it somehow in trying to formulate the main idea. So maybe I write the title beyond the category of sets. It is like this. There are lots of families of curves related by such the morphisms of the kind defined there to the right, and it is some category. Sorry, in the beginning of the course we have agreed to draw it like this. And well, in reality there should be arrows somewhere away from to an object that lies away from this category. So the idea of the fine moduli space is to forget about this fictitious object and to work with the category of families of curves themselves. So as we see, the bases are not seriously restricted. The morphisms are restricted in a very essential way. So we substitute the object of a dream, the moduli space that would behave in a categoric way as we would like, but just work with the topology instead. It is an important particular case of Grothendieck topology, the main object of our course. The goal of today's lecture is to explain how this approach, the approach that moves us from the coarse moduli space to the fine one. Please don't consider it as a mapping or a morphism or a functor. It is neither. It just shows the direction of our thought. So I'd like to try to explain how this direction is realized on the classical level, in the classical mathematics, and not in an arbitrary case, but over complex numbers. Sorry, before we turn to it, perhaps I formulate following Mumford. What do we gain? What are the objects here? So they are the cohomology theory, the results on cohomology that are the most attractive in this field, and I should emphasize that the main is widely open. Then here we mean something like a cohomology with constant coefficients, but there are other, perhaps I write down that for the time being we possess only the partial information, but there are Picard group that are known perfectly, defined. Of course, there we need some effort to redefine the objects from the classical algebraic geometry to topologies, but it was done, and I'm going to mention something else. Well, the last thing to mention is that the definition over, perhaps not Z, but over the spectrum of Z. So here are the direction. I cannot say that it is easier to perform such definitions and calculations for the fine moduli space than for the coarse one. But I hope to persuade the listeners that this approach is more natural than the classical one, and perhaps the future development of the subject that that need some working over will be rather performed in this frame than in the classical one. So this is the general picture and the plan formulated. Any questions now? Саша, где-нибудь видно, сколько участников? Кажется, один, но на что-нибудь еще надо. Один.
Кажется, пока.
Окей. Так что я разговариваю с вами и с теми, кто когда-нибудь, может быть, будет это просматривать. So, any questions about what is written now on the blackboard?
When you say about modularized spaces over spec Z, what do you mean by curves? Family of curves.
What do I mean? Yes, this is a good question, but of course I mean the family of curves in the arithmetic sense, that is, over every prime p, we consider the reductions that define the curves over the algebraic closure of the corresponding finite field.
Oh, okay, I see.
Okay, so now I erase everything. And to the end of today's lecture, we'll assume that the ground field is the field of complex number, and let me remind that the main problem is the mg of C as algebraic variety. It was not yet defined. It was defined as a set, and may I just repeat some strange foundational problem. Suppose we are given a set and lots of with a supposed algebra geometric structure, and we have lots of morphisms from the other quasi-projective varieties to it. In fact, lots of perhaps draw it and J. From now on I omit C since it is assumed, and for every B's, perhaps let me remind you that it is even not a set, that the bases constitute a category, but they have I'm trying to draw the image. They have the perfect algebra geometric structure for today, and until we do not consider the deformation theory that perhaps will be mentioned today, they are just can be assumed to be quasi-projective manifolds. So we have a set, and on the level of forgetting functor from the algebraic varieties, with the not yet defined structure on Mj, we have a lot of morphisms. Perhaps it defines the structure of algebraic variety in a unique way. Well, anyhow, the supply of such mapping should be large enough. However, there is a remaining problem like this to define M sub j, and during the last lecture it was defined as a transcendental real orbifold, but of course it is insufficient and by no means extendable to the arbitrary ground field. So let's try to define, now let's do some classical algebraic geometry, and in fact we'll see that we are somehow forced into the direction of the fine moduli spaces. So we know that here any curve of genus 1 can be defined in, well, generalized, or maybe to be accurate, this is the classical Weierstrass form. Therefore, we see that M sub 1 is, well, the set of the subset of plane my discriminant, well, somewhere 27, somewhere for some time, up to some action of C sub 2. Well, this is almost the moduli space. It is one-dimensional in the obvious way. However, there is no universal family over it. As we see, we can rewrite it in the, well, perhaps let's write that this is Weierstrass form, rewrite it in the Mumford form. I believe that it is like this plus J minus 12 cube over J with a small question mark, maybe a bit differently, J times x plus 1. So here we have all the curves, but well, infinite number of times the whole multiplicative orbit of curves, Here we have all the curves, so this is, I think it is the Bamford form, at least. It can be found in the paper I follow closely. And well, I haven't seen it anywhere else. So here we have the multiplicative orbits of any curve. And this one could be said almost universal. Here we have the G line, and we have just the two singular values here, and everywhere we have over every point we have an elliptic curve, but some nonsense over when G is 12 cube, then what do we have? Formally, we have a semi-cubic curve, but it is of course wrong. The curve with J with this value of J is a curve with a square period, and here it is not defined as an affine curve, though it is a beautiful curve with the rhombus of two equilateral triangles, composed of two equilateral triangles as a fundamental parallelogram. Instead of away from these 2 points, from 2 values of J, it is we have the base of the universal family of elliptic curves. However, these two spoil the whole picture, and in fact, just due to the extra automorphisms in both cases, they explain why we don't have the fine moduli space with in genus 2. However, we consider the third one, that is called, well, x minus 1 and x minus t, that can be called the Legendre cubic. And I would call it hexaversal, because with the over the T line we have a perfect family of cubics everywhere. Well, I have to make a solution how to draw a general cubic. At some point I'd like to draw them as a connected object. Let this be symbolically like this, the picture in between the real and the complex picture. Just number of handles can be drawn, and T is just not allowed to assume 0 and 1 when it becomes the Cartesian folio. This T belongs to what we call M sub 1, and let me put the 2 here. That will be soon explained. M1, 2, that is precisely C double dotted or C minus 0, 1. Now the set theoretical M1 is the result of the factorization of this P1 by the automorphisms of 0, 1, infinity. So here we have the not a universal family of curves of genus 1, but of curves of genus 1 with some additional structure. This additional structure geometrically is defined by the numbering of the points of second order, 3 points of second order. And as for 2 here, I just find some place. Perhaps I erase all the generalities for now. And introduce the one of the central ways towards fine moduli space, that is the modularized modularized spaces. Let me write it: complete spaces with level structure. These are of the level L. L is a natural number being at least 2, consists of the pairs X, C, X, iota, where iota is a fixed isomorphism of the first perhaps homology groups, that is clear X with the coefficients Z over L Z to 2z over L z to G. Such a set over the obvious isomorphism relation, that is, such pairs are isomorphic when the curves are isomorphic, and the isomorphism, the mapping realizing isomorphism induces the fixed isomorphism in the corresponding homology. So then we have the G sub L over M J. It is just a factorization over the spinor group. Well, there is a canonical skew product in the first homology, and SP is the SP to J, and SP respects it. P of to J over Z over LZ. So with varying L, we have a covering of every modular space, and this system of covering is an important piece of the topology we have defined. You can ask why we ignore the bottom of this diagram. I'm unable to draw it with varying L. The answer is that the functor of family just of curves F, as we have decided, is non-representable, while just a bit above, when the isomorphism becomes a little more complicated, it becomes representable. So this is one of the easy steps to get, it is representable just because there are universal families like this one. So this one with L equal 2, it is a very simple family. Simple, I mean, in terms of equations, simple family with just a bit of additional structure. So it solves, it explains the way towards fine modular space for genus 1. Any questions about this construction?
I have two questions. The first one, are we still working over C, and if not, in what sense do I understand this?
Yes, thank you. So over C, of course, this construction is quite general, perhaps away from characteristics 2 and 3, where something special happens. So is there any difference? The answer is that no, just over other fields we should specify what do we mean by homologies. In fact, homology with finite coefficients are perfectly defined over curves, and this is exactly the main idea of étale topology. And we better speak about cohomology. That doesn't change anything essentially. And the base for this definition is just to consider the group of points of order L.
Well, thank you. And the second question is, do I understand correctly that this isomorphism in the definition of the level structure, it should respect some skew symmetric form?
Here in a very good question, it should not be an abstract isomorphism. Yes, I meant it here, and I didn't mention it here. Thank you.
And the form is something like intersection form?
Yes. So here is just, yes, thank you. These even dimensional modules are supplied with the symplectic form. Okay, otherwise, the situation will return to this genus in a while. So let us discuss the next case, the next genus. And here again we can consider the general equation like this. That is quite a direct generalization of the previous equation. And again, we have a family of curves in which every curve is any curve can be found here in 720. That is 6 factorial times. Well, either the generic curve or or we consider them with the appropriate multiplicity. And the reason is that this form means the ordering of the Weierstrass point. It is, here we see curves together with another additional structure, Weierstrass points. It is not just the set, it is the tuple, the order tuple, infinity 0, 1, t sub 1, t sub 2, t sub 3. Of course, by a fractional linear transformation, we can transform any 6 tuple to this form, but to do it in a well-defined way, we need to number them first over the complex number. It is something like this, and we declare that this is the first, this is the second, the third, the fourth, the fifth, and the 6. The curve with its just algebra geometric structure has no natural order on the wire truss point. So here there is no special notation for it like this, and perhaps it cannot be defined in the cohomological terms, but what we have here will will denote mj hat as a working notation for any étale covering of the coarse moduli space. And here we have the étale covering of by S, the symmetry group S6. And again, we have a structure here that is perhaps not extendable to any other genus, because in higher genera the wire truss points sometimes collide. But this is a unique structure. I mean, we can consider the category of curves of genus 2 with numbered wire, with the ordered wire truss point, and with the obvious obviously defined morphisms, and the family functor is again representable by this M2 hat. So the effect, this is just one more example of gaining representability factor by considering additional structure. And again, the general moral is to consider some small, or as we'll see, not so small additional structures. So the bare curve without the bare curves without anything additional do not constitute the category of appropriate objects to be, the families of which can be nicely classified in the categoric sense. As soon as we supply them with some structures, they become classifiable, both in the human sense and in the categorical sense. So I have suggested two kinds of additional structures. Perhaps there are more, perhaps there are some that we are not aware of. And considering the topology that was just introduced today, suggest taking into account all the possible additional structure without trying to consider them all. Sometimes introducing the not so well controlled structures gives a better understanding of objects. This is a more general moral. So, any questions about this?
So the level structure in the second example is something like the chosen order of inflection points. Yes.
I don't know. I'm unable to represent this additional structure, the ordering of Weierstrass points in the cohomological terms. I think this is just another structure. Did I call it level 1? If I did, it was wrong. It is just some additional structure. That's why I've denoted it in some.
And these Weierstrass points are just the inflection points, right?
What is the Weierstrass points?
Yeah.
These are the fixed, as you see, these are the fixed points of the Weierstrass involution. Any curve of genus 2 possesses the only involution, the factor over which is rational. And it has exactly six fixed points. And these are, well, in one form, here are 5 of them and infinity.
Thank you.
Welcome. Okay. Now we have a new situation with when G equals 3. Perhaps here I add one more general topic in understanding both coarse and fine moduli space. Symbolically, it is just the H0 of M. Now we are discussing C. Or, in other words, there is a serious problem of whether the moduli spaces are connected. It is quite an untrivial question. We'll see its non-triviality just now. It starts with genus 3. Well, in the previous 2 genera it was obvious, since, well, I skipped the theorems, the, well, rather deep results, saying that all the curves of the corresponding genera can be presented in the form we have discussed them. So for the higher genera, there are no such obvious forms, and more than that, we are not going to discuss, though of course we could discuss the corresponding theories in the higher dimensions, that is, the moduli spaces of, say, surfaces with fixed invariants. There are just 2 basic invariants of the surface instead of 1 genus that are the Euler characteristics and the square of canonical class. And there the moduli spaces can be defined and are quasi-projective but not connected. So it is not a problem of proving something obvious. It is the important special property of of genus 1 case. And one of the motivations of the paper by Delin and Mumford, where all these concepts were elaborated, was just to prove this result. Well, not connect. They are called the irreducibility of the modular spaces of curves, and they found out that this result, though being considered as correct in the classical Italian geometry, had a wrong proof. It was not, in some perhaps severest paper, that there was found a crucial mistake, and one of the goals of developing this technique, the Grodsendik topology technique, was just to save to construct a new proof of the known fact. I'm speaking about it now because the problem starts with genus 3, and anyhow, in fact, over every field M and J, the curves, well, for any J starting from 3, there are two curves, two subsets of modular space, non-intersecting, the canonical curves and the hyperelliptic curves. In particular, M sub 3 is the smooth plane vortex, up to here the isomorphism is the precise action of PSL. PSL3, acting by fractional linear transformations. Let's write down explicitly the hyperelliptic equations, that is the product of x minus xi for I to 8 over PSL2 that acts on the abscisses of Weierstrass points. So here we have a good families, of course, with the same problems as before, with some that are presented by special fibers with additional symmetries. So here, I should say that both varieties are described by the geometric invariant theory. That is constructed exactly for the problems of this kind. It is a very hard theory. In fact, the description even of hyperelliptic curves, even in the previous genus, give results that are non-practical at all. They are difficult to work with, even with modern computers, and seem quite impossible to work by hands, though in 19th century mathematicians managed to do something. Of course, this one is much harder, but in principle it can be done. But the fact that these two pieces, this one of dimension as it can be calculated of dimension 6, and this one is 8 minus 3. This is of dimension 5. It is by no means an easy problem to stack them together in some unique family. So we easily write down the families, for example, of all the plane quartics or all the hyperelliptic curves. But I would say that even the question whether they can be connected as a unique family is not at all obvious. However, I'm speaking about it as for the motivation now in the remaining small time of the lecture. I'll show the transcendent way of proving that these modular spaces are connected and irreducible. Well, perhaps I would better speak about irreducibility. Of course, they could be, one could imagine the situation where this is one component and there is another one, and they could even, there is a small exercise to show that they cannot intersect. These curves are really canonical ones, and the canonical curve cannot be hyperelliptic. So I wanted to show that the down-to-earth problems of writing down the equations of general curves become harder and harder with growing genus, or in other words, that the straightforward way of supplying moduli, supplying coarse moduli spaces with a structure of quasi-projective variety is perhaps wrong. Perhaps some other approaches are needed, and the other transcendental approach that we start discussing now, definitely I'll have no time to complete it today, gives finally the complex structure. So, any questions about it?
So, particularly we see that the moduli spaces of genus 3 curves is not connected, right?
No, it is. It is. This is just the set theoretical. It is just the set theoretical decomposition. It is connected.
So they are not closed subvarieties.
In the true structure, in the true structure of M3, M sub 3, there is just a divisor of hyperelliptic curves. just a 5-dimensional sub-variety of 6-dimensional variety.
But then I don't understand, because you say that MG can be represented as a union of two closed subvarieties.
Yes, thank you. Thank you. I had to emphasize that set theoretically.
But even said theoretically, if these subvarieties don't have, if they don't intersect, then probably this is the combination.
They do not intersect, but the larger part, for example, for genus 3, the larger 6-dimensional part is just a risky open in the whole M3. It's just a complement to this divisor, the hyperelliptic divisor. In higher genera, hyperelliptic curves constitute the subvarieties of larger codimension.
Okay, and is it known that both parts are irreducible?
Are what?
Irreducible?
Yes.
Okay.
Well, as for the larger part, it is perhaps the larger part are the risky dense in the whole moduli spaces. As for hyperelliptic curves, I would say it is obvious because all of them are like this, just projective, the symmetric powers of projective line vectorized by projective linear transformations.
I see.
Good. So up to now, it is true that the ground field did not play any serious role. However, over C, there is one of the basic Jaja theorem. It is the standard abbreviation of the Serre's paper, Géométrie algébrique et géométrie analytique, that established the equivalence of analytically defined objects over complex numbers with algebraically defined. And the simplest case of it is the so-called Riemann existence theorem. And it tells us that, well, perhaps compact Riemann surfaces we should not perhaps fix the genus, it will be fixed itself up to the isomorphism, and by Riemann surface we mean the smooth Riemann surface here, are in 1 to 1. Well, let me write it down. So, well, we have agreed to call curves just the complete smooth irreducible, or in other words, complete up to equivalence. Here we can understand it like, perhaps write down, to birational automorphism, and we have the notation for it, the discrete, the disjoint union of M sub j of C. So in fact, Riemann's theorem, well, I would say that there is an obvious error, because the algebraic structure defines the complex analytic structure in an obvious way. I'm tempted to write it in the other way, where it becomes quite non-trivial and quite canonical, because it says something that again is not true in the higher dimensions, that is, given quite a transcendental object, maybe a Riemann surface with its conformal structure, then it carries a structure of algebraic curve, which is basically equivalent to the fact that it contains at least one non-trivial meromorphic function. Well, now I see that our time is over, and it is just a point to start it the next time. Just to fix where we are going to start, I fix that the compact Riemann surface is fixed by a conformal structure. Conformal structure. Well, maybe just a couple of words more. Structure. So it can be understood in two ways. First, a Riemannian metric. Up to rescaling, or one should think a bit to understand that this is the same structure as the almost complex structure here. I skip the important point, saying that the compact Riemann surface is not just orientable, it has a canonical orientation, and the almost complex structure is something like a linearization of the true complex structure. I'll just draw it. in any tangent space, there is a fixed operator. So any complex space, tangent space, is supplied by a structure of linear space over C. That means that there is an endomorphism of I, the square of which is opposite to the original tangent vector. And there are two such vectors, but the orientation allows to choose exactly one of them. So this linearized complex structure is called almost complex. Again, in higher dimensions, these are different things, almost complex and complex, while in complex dimension 1, they coincide. The almost complex, or in other words, all the almost complex structures are integrated. Yes, and in fact, the transcendent approach we are going to discuss and to see that it moves us again towards the fine modular space and the system of Étale coverings of the true modular space. So it is realized in terms of the conformal structure. And we'll discuss the details in the next lecture. Any questions, please?
So you're saying that exactly two complex structures induce the same conformal structure, right?
They are the precise synonyms. In both cases, you define the sheaves of holomorphic functions. Up to the behavior in critical points, holomorphic functions are exactly the functions realizing, fixing the conformal mappings.
So these are just the same things, and we can use these terms interchangeably, like conformal structure and complex analytic structure, or not?
Yes.
So that is the same.
Totally. Well.
I mean, for
formally, of course, yes. But the associated structures are different. The conformal structure defines some things that we are not going to discuss here. Spectrum of Laplacians and things like that. Though the complex analytic structure just puts naturally, they are defined, of course, in any dimension, and they extend the algebraic structure over complex numbers. So yes, they are interchangeable and equivalent, but it is a result of some theorem, not just reformulation.
Thank you.
Other questions? Okay, then that's all for today.